This topic video is on statistical significance and variability. Here is where we start talking about p-values and confidence intervals and deciding if research results are meaningful. Take a look at this quick clip to get us started.
Let's assume John tells you he discovered a special dice rolling technique that enables him to roll a 6 more frequently than the average person. To prove it, he rolls a dice in front of you and it actually ends up being 6. However, it's not enough to impress you because it might simply be a matter of luck, as there's a 1 in 6 or roughly 16.7% chance of that happening regardless of which dice rolling technique you use. A researcher who wants to determine if John is right or wrong starts with a so-called null hypothesis, which states that no, there is no relationship between the technique you use and how often you roll a 6. In other words, you start by assuming that John is wrong. John hopes the null hypothesis will be rejected because it would mean it's very likely, even if not 100% certain, that he's right. He ultimately rolls the dice 1,000 times and it lands on 6 in 20% of the cases, so higher than the previously mentioned 1 in 6 odds. Is this enough to negate the null hypothesis? Well, no, because we also have to determine whether the findings are statistically significant. To do this, we calculate the so-called p-value, which is a number between 0 and 1 that lots of applications easily generate for us based on the data we provide. Generally speaking, if the p-value is lower than 0.05, it's a good argument in favor of rejecting the null hypothesis and making John happy. In our case, we'll assume the p-value is 0.04, which is low enough to reject the null hypothesis and kind of like us saying John's 20% success rate is better than the standard 1 in 6 odds, but there's a 4% likelihood this only happened by chance. Therefore, while we cannot be 100% certain John's technique works, we can say that the lower the p-value is, the more certain we are. All in all, here's how things work. 1. Start with a null hypothesis. 2. Gather and interpret data. 3. Calculate the p-value to determine if your findings are statistically significant. 4. If your data supports John's claim and the p-value is lower than 0.05, you will reject the null hypothesis and John will be pleased.
So get your brains focused on this content. Let's refresh ourselves. We consider an outcome statistically significant when the p-value is less than what? The answer, 0.05, which also means, in layman's term, that there is a 5% chance that the result was due to chance. Our objectives for this video are to interpret both p-values and confidence intervals. To get to p-values and confidence intervals, let's start by defining statistical significance. Here we see that statistical significance is a determination made by an analyst that the results in the data are not explainable by chance alone. A result that is statistically significant indicates that there is some kind of relationship between the intervention and the outcome. The outcome is not due to chance. So essentially, what can you do here? You can reject your null hypothesis. So the video we just watched about John and his dice rolling, they found a p-value of 0.04. So they were able to reject the null hypothesis that there is no relationship between the technique and how often John rolls a 6. So if something is statistically significant, we can be confident that we can reject the null hypothesis. But it does not tell us whether the relationship itself is meaningful, just that we can reject the null hypothesis. The measures of statistical significance that we're looking at are p-values and confidence intervals. A p-value tells you the probability of coming to a false positive or a type 1 error. So our p-value is going to tell us the probability of making a false positive claim. P-values are typically pre-assigned as 0.05, meaning that there is a 5% chance that we reject the null hypothesis when the null hypothesis is actually true. So we wrongly reject the null hypothesis. So a p-value does tell us if our result is statistically significant, but it does not provide information on how precise that result is. What I mean by precision is to the degree in which the results would vary if measured multiple times, or the repeatability of the results. That's where our confidence intervals come in. A confidence interval gives you information about how precise the results are. So if we're to repeat a study over and over and under the same conditions, the confidence interval provides for us the information on the level of variability with the repeated study. Confidence intervals, they give us a range of possible results. That is, it tells us what the results might look like if we were to repeat this study. And typically in studies, we're looking at a 95% confidence interval. We will look at examples of that. Utilizing this range of values also will give us information on statistical significance. Again, we will look at that in a bit and practice examples. Journals are increasingly emphasizing this approach to reporting the results. Why? Well, confidence intervals are taking into account the precision of a study. They're not just looking at, here's one study, here's the results. They are statistically looking at what results might look like in repeated studies, which is a lot more pertinent to extrapolate meaningful information. Here's a clip from the Ramapril research article. Take a look at the table and find both the CI and the p-values. Here in this column, you have your confidence interval. Again, it's an interval or in a range of values. We'll look specifically at how to interpret that range and its statistical significance. First, we're going to look at p-values. Here's our column of p-values. Please note that in the study, there are several outcomes, and each of these results has its own CI and has its own p-value. So let's start with p-values and statistical significance. Traditionally, p-value of less than 0.05 is statistically significant. Said another way, a p-value of 0.05 means that there is only a 5% chance that the results are accepted as true when really they are not. P-values, they give us a snapshot of what happened for the specific result within the study. Okay, like the table on the previous page, each outcome had its own p-value. So it's not an entire study that might be statistically significant or insignificant. It is each outcome, each result within the study that is statistically significant or statistically insignificant. That is a verbiage that's often misused when we're talking about a study is we'll say, oh, the study was statistically significant, when an entire study in and of itself cannot be, but each outcome can or cannot be. As we talk about statistical significance, I want you to note that that does not necessarily equate to clinical significance. Just because a result is statistically significant doesn't necessarily make it clinically significant, or even vice versa. If something is clinically significant, maybe it's also not statistically significant within a study. Remember, clinical significance is contextual. You have to ask yourself, what will I do with this information? Is it useful for my practice? Is there a way? Can it be implemented? Again, statistical significance doesn't necessarily mean clinical significance. So here's quick practice. We're looking at an odds ratio of 2.4. The given p-value at 0.09 and a confidence interval of 0.9 to 6.6. Looking at that p-value, is this result statistically significant? P is 0.09. Well, 0.09 is greater than 0.05. That means that this is not statistically significant. These results are statistically insignificant. Let's go back to the table. This is the full table of both primary and secondary outcomes from the Ramapril study. Well, let's just take a peek at our p-values. As we look down the line, we have several p-values that are statistically significant. Here, the death from non-cardiovascular causes is higher than 0.05, so now we are statistically insignificant. And then our secondary outcomes, we have a combination. We have significant, insignificant, significant, insignificant. Okay, again, so our key is it less than 0.05? If it is statistically significant. And each outcome, each result has its own p-value. This table is just a simple summary of p-values and statistical significance. The common language is statistically significant. The meaning means that the result seen is unlikely to be due to chance. Our statistical statement that goes with that is that the null hypothesis is rejected. The conventional threshold, p is less than 0.05. When something is not statistically significant or statistically insignificant, also you might hear non-significant, this means that the results seen could be due to chance. And the null hypothesis cannot be rejected. Here, the p-value is greater than 0.05.
In this video, we're going to talk about confidence intervals and exactly how we should interpret them. And here's a reference I used for some of the information for the examples in here. So let's say that we have a patient who is not doing so well and their blood pressure is low. And we want to try giving them a drug to raise that blood pressure. We have two choices. We have vasopressor A to raise the blood pressure and vasopressor B. And we want to determine which one is better, so we do a trial. And in this trial, we look at two populations. We look at two samples, and one we give vasopressor A, one we give vasopressor B. And the mean increase in blood pressure for vasopressor A was 70, and the mean increase of blood pressure for vasopressor B was 95. So the difference is 25. So then we go through our normal hypothesis testing protocol. We create a null hypothesis that there's no difference, an alternative hypothesis that there is a difference, and we go through the entire process, and then we find out that the p-value is 0.05. So then we say that this is a statistically significant difference, that vasopressor B does increase the blood pressure. And so then we would report this point estimate in our paper that we had a 25 millimeter per mercury increase in blood pressure using vasopressor B as opposed to vasopressor A compared to vasopressor A with a p-value of 0.05, and so it was statistically significant. And that's great, but we can do better by using a confidence interval, and let me show you how. So with a confidence interval, we would report that the value is 25 with a 95% confidence interval that the value is between 5 and 44. And this gives us a lot more information. And what it says is that we are 95% sure that the real value is between 5 and 44. And so the real value could be 5, which is statistically significant. That is, that vasopressor B did increase the blood pressure, but only by 5, so who cares? That is not clinically significant. And it also could have increased the blood pressure by 44, which is a lot. You're like, wow, that thing works great. So you can see already that confidence intervals give you an estimate on whether this effect is clinically significant, whereas the point estimate only told you whether it was statistically significant. And so it gives you much more information than just the p-value does. It also gives you some information on the precision of your estimate. So whereas we might report 25 and 0.05 as our point estimate, for a 95% confidence interval, this could be 5 to 44, or it could be between 20 and 32, which is much more precise, or it could be between 0 and 100, which is less precise. So the confidence intervals also gives us information on precision. It gives you so much more information than just this point estimate with the p-value. Let's look at a few other things first before we go. And the next one is let's look at the different kinds of confidence intervals you can get. And so the more confident you want to be about something, the bigger the interval you're going to have, right? So the more confident I want to know about the difference, in order to be more confident that my interval is going to contain it, I have to have a bigger interval, right? So if I'm willing to be less confident, I can have a smaller interval. And another point that you can see here is that for this 99% confidence interval, the point of no difference, that is a value of 0, is included in here. So you cannot say with 99% confidence that there's a difference between vasopressor A and vasopressor B, because the value could certainly be 0. And it could actually be worse, right? It could be -5. It could actually, vasopressor A could actually do better than vasopressor B. So let's talk about this point of no difference a little bit more. And when you're comparing things, you're going to look at two different methods, subtraction and division. So when you subtract two things that are the same, you get the same minus the same, you get 0. That's when there's no difference. When you divide two things that are the same thing divided by the same thing, you get 1. So subtractions are things like we compared in our example here with the blood pressure, but could it be other things like risk reduction? So anything that includes the word difference or reduction in it. Now for division, we're looking for things like odds ratio or risk ratios. So you're looking for things that include the word ratio in it. So if a parameter is listed and it's a subtraction type thing, like maybe they say the difference is 25 with a 99% confidence interval of -5 to 78, you look at the confidence interval and you say, hey, that includes the point of no difference. And so that is not statistically significant. Similarly, if you're looking at a ratio type comparison, then you would look at the, and let's say they had an odds ratio of 4 with a 99% confidence interval of 0.2 to 7, you would say, hey, the point of no difference is in there. So this thing is not statistically significant. So again, let me stress that point. When you're looking at confidence intervals, think about what is the point of no difference. If it's a subtraction type problem, the point of no difference is 0. If it's a division type problem, the point of no difference is 1. And we know we can recognize a division type problem because it'll usually have the word ratio in it. And we'll recognize the subtraction type problem because it'll usually have the words like reduction or difference in it. And if the confidence interval includes this point of no difference, 0 for subtraction type problems and 1 for division type problems, then you don't have statistical significance. And so you can see that confidence intervals tells us so much more than point estimates with a p-value does. And so you're going to see these reported more and more often in journals instead of p-values and hypothesis testing, because the confidence intervals can give you an estimate of the precision. It can also tell you whether something is potentially clinically significant versus only being statistically significant. It tells you other things as well, but just remember the thing that you want to look at here in order to determine whether something is statistically significant or not is, does the confidence interval include the point of no difference? And we looked at that. Subtraction is 0, division is 1. That is the point of no difference. If it includes that point, then it is not statistically significant. All right, thanks for watching. Bye.
To discuss variability in confidence intervals, we'll look at this simple example of a weight loss study. Here our treatment group has a mean weight loss of 10, our control of 3, making a group difference of positive 7, and we see our confidence interval of being 2 to 12. The true estimated effect of the intervention is best represented by a range, that 2 to 12, or the confidence interval. Same as our p-value, a confidence interval goes with a specific outcome or a specific result. It doesn't go with an entire study, but each outcome in that study. Confidence intervals provide a range of values, which helps assess the precision of the results. The wider the range, the more variability. The more narrow the range, the more consistent. You saw in that video looking at different confidence intervals, 90, 95, and 99%. That 99% had a very wide range. To be 99% confident, we have to extend that range. To be just 90% confident, we have a more narrow range of values. For the most part, confidence intervals are defined at 95%. If we repeated the study 100 times, the results that correspond with the confidence interval would fall somewhere in those ranges 95 of the 100 times. Let's talk about the value of no effect. That was discussed in the video as well. That value that means no effect is that value in which intervention is having no effect on the outcome. In the previous lesson, we looked at difference statistics and ratio statistics. And in our difference statistics, when intervention and control had the same value, when we subtract that value from itself, 10 minus 10, we get 0. That is the value of no effect in different statistics. In ratio statistics, if you have the same value, 10 divided by 10, our value of no effect, 1. How does this relate to confidence intervals? Let's look at it. When you are looking at your confidence interval, if within that range falls the value of no effect, then your p-value is statistically insignificant. So why is this? When you are on the negative side of the value of no effect, then the benefit is actually favoring the opposite group. So if sometimes the benefit favors the intervention group, but sometimes it favors the control group, the benefit is not consistent enough to say that this is repeatable. So if I go and repeat the study tomorrow and 100 other times, there's no predicting which group will have a better outcome. Looking at our simple example of the weight loss study, our CI is 2 to 12. Our results are represented in a difference, in a subtraction. What's our value of no effect in subtraction? The same number minus the same number, 0. Okay, so we're asking ourselves in the CI 2 to 12, is 0 included in that range of numbers? No. So because 0 is not included, the value of no effect is not included in our range. When we repeat our result at a 95% confidence interval, the benefit is to the intervention group every time. So is our p-value statistically significant? Yes, because 0, our value of no effect, is not in your confidence interval. So I can look at my CI without looking at my p-value and infer my p-value will be less than 0.05. All right, this one's for you. This comes out of a table that we've actually seen previously, the effect of vitamin D3 on severe asthma exacerbations. Tell me a little bit about the p-value here. So looking at days to severe exacerbation, my group difference of -13, here I have a confidence interval of negative 42.6 to 16.2. As I'm processing, first I'm looking at, okay, how is the result given? It's given in a difference. And a difference, the value of no effect, is 0. Is that value of no effect included in the range of the confidence interval? Yes. Therefore, our p-value is not significant. I don't know what it is, but I know it's greater than 0.05. I can briefly look at the ones below our circled one. Again, all of them as a difference include 0, so the p-value will be greater than 0.05. Both of those examples were with differences. Now let's look at a ratio. So remember, with a ratio as our provided result, we're looking at division. So 10 divided by 10, the same number divided by itself equals 1. So now we're looking to see if the confidence interval includes 1. Back to this little clip that we've utilized. Here we have a 95% confidence interval of 0.9 to 6.6. And this one, you really have to take note. This is an OR, an odds ratio. So to infer our p-value, we're looking at a ratio at division, so our value of no effect is 1. Does our range, our confidence interval, include the value 1? Yes, it does. It's quite close to 1, 0.9, but it does include our value 1, so we would expect, which you can see right there, that our p-value is greater than 0.05. It's pretty close, but it's greater than. So here I'm going to have you put this all together. Are these outcomes statistically significant? Go through each one. Can you figure it out? We don't need to know the p-value. We have a confidence interval. So we're looking at the confidence interval here. The next thing we need to find is how are these results reported? Because we need to know what the value of no effect is. Are they difference statistics or are they ratio statistics? Looking at this table, we see the type of effect estimate. HR, hazard ratio. RD, risk difference. So we have both ratio and difference here. So we have two ways to look at our statistical significance. I'm going to let you go from there and see if you get them right. So if you got all of those right and know exactly how we got there, you're done. You can shut off this video. If you didn't quite follow along, don't know how we got to those conclusions, I'll do a quick explanation. Our primary outcome, the p-value, yes, it is significant at 0.041. Here we're looking at a hazard ratio. Ratio, the value of no effect is 1. And here our confidence interval, 1.01 to 1.42. 1 is not included within our confidence interval. And because the value of no effect is not included, I don't know my exact p-value, but I do know my p-value is significant, less than 0.05. Okay, one more here. This secondary outcome where we get a p-value of 0.13. Here we're looking at a difference, a risk difference. Our confidence interval is negative 1.5 to 11.1. When we're looking at a difference, our value of no effect is 0. Subtraction. Is 0 included in this range? Yes, it is. Therefore, I know my p-value is not significant, greater than 0.05. That concludes our discussion on statistical significance, p-values, and confidence intervals. Please reach out to me for any help, any inquiries, and keep trucking along.